The critical point is a point on the phase diagram where the liquid and gas phases become indistinguishable. The critical point can also be defined as the point on the phase diagram where the liquid-to-gas surface tension of the substance becomes equal to zero. A third definition of the critical point is the point on the phase diagram where the heat of vaporization is equal to zero. There are some interesting things that happen at temperatures and pressures that are higher than the critical temperature and pressure, and we will study them next. Consider two piston cylinder arrangements that contain the same liquid substance, at the same temperature, but at different pressures. The pressure in the tank on the left is smaller than the critical pressure, and its initial condition on the phase diagram is denoted by the hollow circle symbol. The pressure in the tank on the right side is larger than the critical pressure, and its initial condition on the phase diagram is denoted by the solid circle symbol. Let's now study what will happen if both tanks are heated to a higher temperature. For the tank that is at a lower pressure than the critical pressure, as we have seen before, when the liquid is heated, it will first turn into a liquid-vapor mixture, with a distinct separation between the two. Then as more heat is added at constant temperature, it will eventually become pure vapor. Further heating increases the temperature and specific volume of the vapor. For the tank that is at a higher pressure than the critical pressure, on the other hand, when the liquid is heated, there is a continuous phase change from liquid to gas, without any liquid-gas meniscus. We can then conclude that, as can be seen from the intersection curve of the shown constant pressure plane with the phase diagram, isobaric heating or cooling of a liquid whose pressure is lower than the critical pressure results in a distinct phase change, with a liquid-gas meniscus. And second, isobaric heating or cooling of a liquid whose pressure is higher than the critical pressure results in a continuous phase change, without a liquid-gas meniscus. You can now drag the sliders, or drag the pistons themselves, for both tanks, to change the condition of the substance, and observe how that affects the 2D and 3D phase diagrams and the piston cylinder simulations. Consider two piston cylinder arrangements that contain the same liquid substance, at the same specific volume, but at different temperatures. The temperature in the tank on the left-hand side is smaller than the critical temperature, and its initial condition on the phase diagram is denoted by the hollow circle symbol. The temperature in the tank on the right side is larger than the critical temperature, and its initial condition on the phase diagram is denoted by the solid circle symbol. Let's now study what will happen if both tanks are compressed to a higher pressure. For the tank that is at a lower temperature than the critical temperature, as we have seen before, when the vapor is compressed, it will first turn into a liquid-vapor mixture, with a distinct separation between the two. Then as the heat of vaporization is released from the substance at constant pressure, it will eventually become pure liquid. Further compression increases the pressure and decreases the specific volume of the liquid. For the tank that is at a higher temperature than the critical temperature, on the other hand, when the gas is compressed, it remains a gas and does not change phase. We can then conclude that, as can be seen from the intersection curve of the shown constant pressure plane with the phase diagram, isothermal compression of a gas that is at a lower temperature than the critical temperature results in distinct phase changes. And second, isothermal compression of a gas that is at a higher temperature than the critical temperature does not result in a phase change into a liquid. You can now drag the sliders for both tanks, or just drag the pistons, to change the condition of the substance, and observe how that affects the 2D and 3D phase diagrams and the piston cylinder simulations. When you wish to continue with the lecture, press the play button at the very top. From the previous discussion, we can now identify the similarities and differences between the gas and a vapor. The vapor and gas states of a substance are both gaseous phases of that substance that are characterized by relatively large separation distances, and little interaction between the molecules of the substance. Yet when the vapor state is compressed at constant temperature, its phase changes into a liquid. For the gas state, on the other hand, when it is compressed at constant temperature, it does not undergo a phase change. Now let's turn our attention to the liquid-vapor mixture. The quality of a point in the liquid-vapor mixture is also called the dryness factor, and is usually represented by the symbol x. The quality is equal to the mass of the vapor divided by the total mass of the substance, where the total substance mass is equal to the mass of the vapor plus the mass of the liquid. So in other words, the quality at any point in the liquid-vapor mixture is a number between 0 and 1, representing the amount of vapor that is in the liquid-vapor mixture. The quality of saturated liquid, which exists on the curve that separates the liquid phase from the liquid-vapor mixture region, is equal to 0, for all liquid. On the other hand, the quality of saturated vapor, which exists on the curve that separates the vapor phase from the liquid-vapor mixture region, is equal to 1, for all vapor. The quality of any other point inside the liquid-vapor region will be between 0 and 1. Of course, it is meaningless to speak of quality outside of the liquid-vapor mixture region. Suppose we have a liquid-vapor mixture, as shown here. In this section, we will learn that for any point in the liquid-vapor region, we can find the mixture mass-specific property, or mixture per unit mass property. For example, to find the specific volume at this point inside the liquid-vapor region, we need to know the following: 1. The quality, X at that point; 2. The mass-specific volume of the vapor, at the same temperature and pressure, represented by this point on the right, at the intersection between the liquid-vapor and vapor regions; and 3. The mass-specific volume of the liquid, at the same temperature and pressure, represented by this point on the left, at the intersection between the liquid-vapor and liquid regions. If you connect the 3 points, you'll see that they lie along a horizontal line, indicating that they are all at the same temperature and pressure. Let's derive an equation which will use the quality variable to obtain the mixture mass-specific properties, or mixture per unit mass properties, for any point in a liquid-vapor mixture. The total mixture volume is equal to the volume of the vapor in the mixture, plus the volume of the liquid in the mixture. And, since volume is equal to the mass times the mass-specific volume, we can replace each volume with its respective mass times its respective mass-specific volume. Hence the total mass times the mixture mass-specific volume is equal to the mass of the vapor times the mass-specific volume of the vapor, plus the mass of the liquid times the mass-specific volume of the liquid, where the mass-specific volume of the vapor is represented by the shown point on the phase diagram, and the mass-specific volume of the liquid is represented by that shown point on the phase diagram. We can then replace the mass of the liquid by the total mass minus the mass of the vapor, and we have the shown expression. Then we divide both sides of the equation by the total mass, and then simplifying we get this equation. Since the quality variable X is equal to the mass of the vapor divided by the total mass, we can make the substitution for X, and then simplifying, we get that the mixture mass-specific volume is equal to the quality times the mass-specific volume of the vapor, plus 1 minus the quality times the mass-specific volume of the liquid. Previously we found an equation for the mixture mass-specific volume at a given point in a liquid-vapor mixture, which uses the quality at that point, and the mass-specific volume of the vapor at the same temperature and pressure, and the mass-specific volume of the liquid, also at the same temperature and pressure. This equation works for any point in the liquid-vapor mixture. Let's take another point, for example this point. Draw a horizontal line through the point, and find the 2 points along that line that are on the border of the vapor region and the liquid region. The quality times the mass-specific volume of the vapor, plus 1 minus the quality times the mass-specific volume of the liquid, give you the mixture mass-specific value. From this equation we can see that for a quality value that is equal to 1, the mixture mass-specific volume is equal to the vapor mass-specific volume. For a quality value that is equal to 0, the mixture mass-specific volume is equal to the liquid mass-specific volume. The same method that we have outlined can be used to obtain other mixture mass-specific properties. For example, the mixture mass-specific internal energy of a vapor-liquid mixture is equal to the quality times the mass-specific internal energy of the vapor at the same temperature and pressure, plus 1 minus the quality times the mass-specific internal energy of the liquid at the same temperature and pressure. When a solid that is at a constant pressure, that is lower than the triple line pressure, is heated, it transforms directly into a vapor without passing through the liquid phase, in a process known as sublimation. This can be seen by examining how a constant pressure line at this pressure intersects the two-dimensional pressure versus temperature diagram, and how a plane of constant pressure intersects the three-dimensional surface of the phase diagram, without passing through the liquid region. In this case, as the solid is heated, it will initially expand, with an increase in its specific volume. Then, when this point is reached, the solid starts to sublimate at constant temperature, while absorbing the latent heat of sublimation. When we reach that point on the phase diagram, all the substance has transformed into a vapor. Further heating results in the expansion of that vapor as its specific volume increases. Of course, the reverse process is also possible by cooling the vapor that is at that pressure. You can now drag the slider or piston to change the condition of the substance, and observe how that affects the 2D and 3D phase diagram and the piston cylinder simulation. When you wish to continue with the lecture, press the play button at the very top. When a solid that is at a constant temperature, that is lower than the triple line temperature, is expanded, it transforms directly into a vapor without passing through the liquid phase, in a process known as sublimation. This can be seen by examining how a temperature isotherm at this temperature intersects the two-dimensional pressure versus specific volume diagram, and how a plane of constant temperature intersects the three-dimensional surface of the phase diagram. In this case, as the solid is expanded, its pressure decreases, while its specific volume increases. Then, when this point is reached, the solid starts to sublimate at constant pressure, while absorbing the latent heat of sublimation. When we reach that point on the phase diagram, all the substance has transformed into a vapor. Further expansion results in the lowering of the pressure of that vapor as its specific volume increases. Of course, the reverse process is also possible by compressing the vapor that is at that pressure. You can now drag the slider or piston to change the condition of the substance, and observe how that affects the 2D and 3D phase diagram and the piston cylinder simulation. When you wish to continue with the lecture, press the play button at the very top. The triple line is a line on the phase diagram that denotes the condition at which all three phases, namely, the solid, liquid, and vapor phases, can coexist in equilibrium.